In section 6.2, we talk about the number of elements in a finite set. So in other words, a set that is countable. This is part 1. In probability, which is our next chapter, chapter 7, we will need to find the number of elements in a set. The number of elements in a finite set is determined by simply counting the number of elements. So the notation that we're going to use is this. So if we're looking at a set A, then n of A means simply the number of elements in A. So means the number of elements in A. So we're going to start off with a nice example. So we're going to let A be the set 1, 2, 3. B is the set 4, 5. So 4 and 5. And then finally the universe, which is really important for where we're headed, is 1 through 7. So 1, 2, 3, 4, 5, 6, and 7. Okay, so what we want to find, first of all, in our first example, is the number of elements in A. Literally, all you have to do is count them. So it has 1, 2, 3 elements. So the number of elements in A is 3. Part B is asking for the number of elements in B. Well, we count 1, 2. B has 2 elements inside of it, so the number of elements in B is 2. Don't make it any more complicated than that. Part C is asking us for the number of elements in A plus the number of elements in B. Well, literally, we're just going to take the 3 we found here and the 2 we found here and get a 5. So there are 5 things altogether in A plus B. Part D is reiterating that. It's asking for the number of elements in A union B. Okay, well, A union B is everything in both A and B. So we would have a 1, a 2, a 3, a 4, and a 5. And altogether, that would be 5 elements. We're going to notice these 2 answers are the same. That comes back in a minute as a theorem. Part E is asking for the number of elements in their intersection. Wait a minute, A and B have nothing in common. Their intersection is empty. So over here, we'll just make a comment that A intersect B is the empty set. So that number is 0 because it is the empty set. F is asking you to find the number of elements in A complement. Okay, so what's outside of A? So A contains this one, and this one, the 1, the 2, and 3. So outside of A is the 4, 5, 6, 7. Well, that's 1, 2, 3, 4 elements. So there are 4 elements that are not inside of A in our universe. Part G is asking us to find the number in A complement union B. So A complement union B. So I think what we really need to do is make sure we're listing out A complement. So let's go do that really quick. So A complement, just to make sure we're all communicating, would be the 4, the 5, the 6, and the 7. So this one's asking us to union this set with this set and then count how many things are in it. Well, 4 and 5 are already listed up here. That's a subset of this set. So when we go to count them, we don't have to count them twice. So we have 1, 2, 3, 4. So the number in A complement union with B is 4. And then finally, part H on that problem is asking us to find the number in A complement intersected with B. So here's A complement, here's B. What do they have in common? Well, the 4 and the 5 is in both. That's their intersection. And that is 2 elements. So then from that work, we can write a theorem. And our theorem simply states that A and B are disjoint. So what we're saying is that the number in A intersect B is 0. And that's telling us they're disjoint, no overlap. Then sure enough, the number in A union B is simply equal to the number in A plus the number in B, which is what we proved right here. So that statement is backed up by this work that we did. Okay, in our next example, they're no longer going to be disjoint. So how does that impact what we're doing? So let's do another example. But this time A and B are going to have an overlap. So our next example says let A equal B. Well, I'm sorry. We're going to let A equal the set 1, 2, 3. We're going to let B be the set 3 and 4. And then finally, the universe is still the same. it's still 1 through 7. So 1, 2, 3, 4, 5, 6, and 7. Okay, some of the stuff we're finding is going to be the same thing. So first of all, how many elements are in A? Well, we can count it up and see that there are 3. How many elements are in B? We can count that up and see that there are 2. Part C says how many are in A plus how many are in B. We're simply going to add our answers together and get a 5, just like we did last time. Okay, part D is asking for the number in A union B. Okay, wait a minute. If I come in and actually physically find A union B, union is everything. Everything in both sets would be the 1, 2, 3, and 4. We don't list the 3 twice because we don't have to list repeated elements. So this time the union only has 4 elements in it, not 5 like we had before. And the reason is because there's an overlap. So E simply says that the number in A intersect B is equal to, well, let's go find it really quick. A intersect B, what do these 2 sets have in common? They both contain a 3. So for us, the number in the intersection is 1. So then we have a theorem at the bottom of that page that says, notice that A and B are not disjoint. They have an overlap. So then the number in A union B is equal to the number in A plus the number in B minus the number in the intersection. And this makes some sense because this 3 was counted as part of A and it was also counted as part of B. So when we counted them individually, it got double counted as part of both of them. So we already know that the union contains 4. A had 3 elements, B had 2 elements. But if we take away the overlap, then sure enough, 4 is equal to 3 plus 2, which is 5, minus 1, which gives us 4. We get 4 equal to 4. So all this is saying is that if you double count something because it's part of both sets, you simply subtract one of those back off.